Hello, welcome to CS61B Discussion 3 for Spring 2022. Some announcements to get out of the way. Most of these are no longer applicable, assuming this video comes out after the solutions come out. The big ones that are still relevant is that the weekly surveys are in fact worth points. A lot of you haven't done the second one. They're easy points, so please, please, please do the survey. We do read every response. We do change the way the course is run based on these responses, such as in the past, we have started making videos that you guys see for homework and lab that help you get started because we noticed that people were expressing that it was hard to figure out how to start those assignments. So please fill it out. Your feedback is invaluable to us. Otherwise, we have a topical review session on Java this Friday in the second floor of SODA in the lab rooms. So if you're feeling kind of behind on Java, if you're feeling like you're not quite getting how to write Java code, this is a great resource for that. Let's get into review. So if you went to lecture, you would have heard Professor Hilfinger talk about simple containers versus structured containers. Now, that terminology might be confusing. The general way to understand the difference is that simple containers are the variables in the sense that you see when you're writing code. So in this example, Marty would be some sort of variable that you have in your code somewhere, right? And so simple containers are small. They're in one part of your computer's memory for this function. All of your little variables are there. Now the problem is when we create a simple container, we want to tell the computer what size we need that container to be from the get-go, because the way Java works is that it allocates the exact amount of size that we need for that container in the beginning. The problem is things like objects can be variable sizes, right? Like, let's say this cat object had an array in it, and until you initialize the cat object, you don't know how big that you want to initialize that array to, but that means that you don't know how big to make the box to put in that variable. And so what we do instead is that we keep these structured containers, which include things like objects, like linked lists, like classes, like arrays. We keep them in a separate part of our memory, and we consider them to be anonymous because the only way to reach them is by going through a simple container, which contains a pointer to that structured container. So to summarize, these simple containers can contain things like numbers. So there's a couple different types of numbers in Java. There's bytes, shorts, ints, doubles, long, floats. If you're curious about what each of these do, you can kind of look that up. Letters like characters, booleans, and then pointers to where a structured container is stored, and null, which is like nothing. Everything else is in a structured container. And structured containers can contain simple containers. So this cat structured container, for example, contains two simple containers, one which is called ID, one which is called age. They're both named, and these happen to both contain numbers. So they're kind of in this box. Next, we can talk about linked lists and arrays. So this week, we're going to be focusing on linked lists. Next week, we'll be talking more about arrays, but linked lists are data structures that consist of structured containers. So each one of these little two-box module node things is a linked list, and it contains two simple containers, a head and a tail. You could also, there's different names for them. Sometimes they're called first and rest or first and next, but let's just call it head and tail here. The head contains some value. So this might be a number, this might be a pointer to some object, this might be a character, and the tail contains a pointer to the next int list or the next linked list. Arrays, on the other hand, are data structures that just hold like a list or a bunch of simple containers of the exact same type of value. So whereas linked lists, technically you could point this at a linked list that contains a letter, for example. Arrays, everything has to be the same type, because we pre-allocate these blocks when we create the array in the first place. Now, there are pros and cons to using each. So linked lists, the pro here is that insertion and deletion is very fast. Unlike Python, in Java, arrays, once we create them, you cannot make them bigger or smaller. To do that, you have to create a whole new array and then copy all of your stuff over. So linked lists in that front are easier to do. On the other hand, arrays are faster. So the trick with a linked list, if you want to get like the 8th item, you have to basically follow 8 pointers and track down that 8th item in your memory. On the other hand, in arrays, because they're kind of a contiguous block that's pre-allocated, all you have to do is say, okay, how big are the values we're holding times how many values are we trying to get. So if we want the 8th item, we'll say like whatever the size of an int is times 8, and we just add that to the beginning, and that's exactly where our integer will be. So arrays are faster in some cases, but linked lists tend to be more flexible, and there are cases where you'd want to use each over the other. Lastly, let's talk about destructive versus non-destructive operations, because we are going to see some problems on that. So Java is pass by value, which means you are passing in a copy of the value of the variable. So here, let's say we have this a variable. It is pointing at this array, because like we said, arrays are structured containers. They are anonymous. So when we pass a into f, what we're doing is we're taking a copy of whatever is in the square. Now, what's in the square is a pointer. Now, in all of my slides, I'm going to represent pointers as arrows because that's a good way to visualize. But you have to remember that in reality, pointers are, in fact, memory addresses. They're numbers. So what's in the square is an address to go find the structured container. So we're going to copy that address over into this x variable within function f, and now we have another pointer to the same object. So in that way, destructive functions are any functions that alter this object, because these changes will persist even after the function is done running. On the other hand, non-destructive functions don't alter any of the structured containers passed in. They are completely allowed to mess with any of the variables, the simple containers that are created within the function, or any structured containers created within the function. They just can't permanently modify any of the structured containers that are passed in. This is a very important distinction. I will say that on tests, it's super common for it to come up where they'll be like, write this function in a destructive way, now write this function in a non-destructive way. So make sure you're clear on the difference and what that means. Next, let's get into the worksheet. So first, we're going to do a box and pointer diagram for these lines of code. And I will give you a minute to think about it, and then we can talk about it together. Okay, let's go over this. So first things first, we have this intlist.list. So like I said before, int lists themselves are like an individual block of just head and tail. So creating an int list with all these items would usually take 4 lines of code. You have to create this one, create this one, create this one, create this one, and then while you're creating them, you can link them all up. That's a lot of work. So we have this static function called intlist.list that takes in a list of numbers and does it for us. So what that looks like is this. We have this L right here that's pointing at 1, 2, 3, and then 4. The 4 is pointing at nothing, which we symbolize by crossing that box. It's a null pointer. Now we want intlist.m to point at l.tail.tail. So it's really easy in these problems to end up with off by 1 errors. The best way, in my opinion, to avoid that is to make sure you're thinking of the objects in terms of pointers rather than in terms of the objects themselves. So what I mean by that is that when we say L, what we're referring to is the value inside this box. So if we said intlist m equals L, what we would be doing is copying the value in this box over into a new variable, which would result in having another pointer to this first int list. That's not what we're doing, but that's how that would be if that was the case. So this is L. So L.tail is the tail of what our object this is pointing at. So that would be this field right here. This variable is L.tail. Whatever's in it is what we would copy over if we were copying over this specifically. And then we do that same thing again. L.tail.tail is this field. It's this variable right here. The second one. So that's what we're going to be copying over into intless.m. Let me quickly change this into a laser pointer. Okay, yeah, that's better. So this is what we're going to be copying over into m, which looks like this, because remember, this is pointing at 3. This pointer, we're just taking this end of it and dragging it down here, and it's going to be pointing at the same object that this L.tail is pointing at, which is this 3. Next, we have n equals intless.list 567. That's just creating an int list the normal way. So we do the same thing that we did in line 1. So now we're on line 4, and we have n.tail.tail.tail equals n. So we're going to do the same thing. So n is just this field right here. So we know what that is. n.tail.tail.tail. So this is n. This is n.tail. This is n.tail.tail, and this is n.tail.tail.tail. So we're going to copy over the value that's in this simple container over into this simple container. So the 7 is going to be pointing back around to this 5. Next, we're going to be doing L.tail.tail equals n.tail.tail.tail.tail. So what that means is we start at n.tail, that's the first .tail, the second .tail, the third .tail, and then we go wrap around again, so now this is the fourth .tail. So the pointer that we're going to be copying over is this pointer, the one that points at the 6th int list. And we're going to be copying over that into L.tail.tail, so that's L.tail, and then L.tail.tail. So this 2 int list tail is now going to point at this 6, which looks just like this. Lastly, we have m.tail.tail equals L. So m is this pointer, m.tail is this pointer, m.tail.tail is that pointer, and it's going to point at whatever this pointer is pointing at. So that means this 4 is going to point back at this 1, just like that. And that is our final box and pointer diagram. Let's try one more. So this time, similar idea, just slightly different. And it looks like I gave you the first one already here. So I'll give you a chance to think about what the box and pointer diagram would look like, the final one would look like here, and then we can talk about it again the same way. Okay, let's go over it together. So like I said, I gave you that first one, that first line. So we start off with 1, 2, 3, made the same way as before. In this line 2, we get to see something that's made the more traditional way. This is going to make a single int list node. So it's going to have a head of 4, and the tail is going to point at L1.tail. And what is that? This is L1, this is L1.tail, so it's going to be pointing at this 2 node, just like that. Now we're going to set L2.tail.head to be 13. So L2 is this pointer, L2.tail is this pointer, L2.tail.head is this number right here. So this 2 is going to change into a 13. Next, we're going to do L1.tail. So L1 right here, L1.tail is right here, L1.tail.tail is here, and L1.tail.tail.tail is this field. So we're going to set this field to be this equal to whatever this pointer is right now. So it's pointing at this 4 node. So we're going to point at the same thing. And then now we're going to create a new int list L3. So this one is just 50, just like that. And then once we're done there, we are going to do L2.tail.tail equals L3. So L2 is this field, L2.tail is this field, L2.tail.tail is this field, and we're going to point that field at whatever this field is currently pointing at. So that's this 50 right here. We're going to be moving our pointer down here. If you notice, this last 3 node is no longer accessible at all. There's no way for us to reach it, so Java will actually kill it. It'll do something called garbage collection, and it'll basically, that memory will be freed up so that we can use it for something else. I'm not sure why this slide is already giving the answer, but we can just talk about the answer here. So is this method destructive or non-destructive, and why? So like we talked about earlier, the idea behind a destructive method is that we don't want to, a destructive method modifies the int list that this variable points at. So this doesn't happen during this function. So here we're creating a new int and we're copying over the value of L dot head into this list head. That doesn't do any modification to L. And here we are assigning L to a new int list. Now, this changes the pointer for L itself, but it doesn't change the pointer it doesn't change anything about the int list that this used to point at, right? So whatever was pointing at that int list outside of this function will continue pointing at it. And now L is just being redirected to a new int list. As a result, when we exit out of this function, nothing will have happened to that int list we originally passed in, so the method is non-destructive. Moving on, let's talk about how to reverse a list. So here we want to implement a function called reverse non-destructive, that's key, such that it returns a new list with all of the elements of L in reverse order. So I'll give you a chance to think about how that could happen, and then we will talk about it together. Okay, let's talk about it. So first things first, we know we don't want to modify the list we're passing in, but we do need to return some int lists. So let's create a new list so that we don't end up modifying the old one. We're going to start with the set to null, and I'm just going to call it return list, but you can call it whatever you want. Next, how are we going to do this? How logically could we do this? So we can't traverse L backwards because it's singly linked, right? There's no way to go backwards once we get to the end. So how could we possibly get the elements in reverse? Well, what if we just built our list backwards? So the idea here is that our pointer starts at the beginning of the list, and we copy that element over into our return list. And then when we move that pointer down, instead of inserting the element in the back of the list, we'll insert it in the front. And by doing that, we'll build our list backwards. We don't have to go through the entire example. We can just talk about how that translates into code. So this while loop keeps going until L is equal to null. This is just a check to make sure that we haven't run out of list yet. Because once we run out of list, there's no point. We don't want to be inserting nulls at the beginning. Next, we're going to do that insertion in the front that we talked about. So we're going to create a new int list. Its head is going to be the head of whatever L int list that we're currently on. And its tail is going to be the list that we've already built up. And so that is going to be exactly what we just talked about. And then next, we're going to move the pointer into the next item in line. And then we're going to keep doing that until we run out of int list L. Lastly, all we have to do is return our new populated int list, and we're done. Just like that. So now, let's do it destructively. So again, we're getting passed in an int list L. This time, I want you to see if you can do it in a way that is destructive. So we want to replace the int list L that we were passed in with the same elements but in reverse. And I'll give you a minute to think about it. Okay, let's go over it together. So since this one's destructive, let's try something recursive because it'll just make more sense. There's probably ways to do this iteratively, but I want to do this recursively. So as always with recursive stuff, first thing we do is base case. If the list is null, there's nothing to reverse, so we just have to call it and say, here is our return L, just like that. Now, how are we going to approach the recursive call here? So let's assume that we already have a method that can reverse the rest of the list that we're on. So for the one, we're focusing on a single node within this int list right now. Where would this node go in relation to the first element? It would go before it. So we insert the reversed rest of the list ahead of our first element, and then the full list would be reversed. So if that was confusing, let's go over it one more time. So let's assume we already have we know how to reverse the rest of our list. So let's say we have our list, we have our first item, and then we have the rest of the list. We know how to reverse the rest of the list somehow magically. Where would this rest of the list go in relation to our first element, right? Our first element will have to be the last element now, so this reversed list should go right before it. So all we have to do is insert that reversed rest of the list ahead of our first element, and then the full list will be reversed. And then we can do that recursively because every int list is a int list that has a first item and then the rest. So we can start here. We are just going to assume that this works. So let's say we have an int list reversed, and then that reverses destructively the L.tail, the rest of our list. And we have to make sure that we're careful that all of our pointers are taken care of here because it's a little bit complicated. So this is what our list looks like right now. So if reverse destructive was successfully called an L.tail, we'll get this. So keep in mind it was darkest to lightest. Now the light and the medium dark have switched places because the rest of our list has been successfully swapped. Notice here the first element is still going to be pointed at what used to be after it because we haven't done any modifications. We passed in L.tail, so it didn't do any modifications to that first item yet. Before we change that pointer, before we lose access to that item, we want to make sure that we put our list in that right spot. So our element is going to go right after that element now. So we just have to do L.tail equals L. So L is this pointer to this item, L.tail is the pointer to this item, and we want to set L.tail to be equal to this first item, to be pointed at this first item. And now that we've done that, we can get rid of that old pointer because it doesn't make much sense to keep it anymore. We want this to be the end, so we want to set L.tail to be equal to null, in case our node is the last one. If it's not the last one, then this will be replaced when we go up a recursive call, just like it was here. If you notice, previously this had a tail of null, and then we replaced it with a pointer to the appropriate element in this recursive call. And then we just return reverse. And we can trust, based on our recursive leap of faith, that it will reverse appropriately in the steps above it, just as it recursed appropriately in this step and the steps below it. There is a slight problem though. If we wait until L is null to end, we risk trying to call L.tail on null, which could error. If you're confused why this is the case, I recommend you try drawing it out and seeing how that would happen. So instead, we have to modify our case to just an easy fix where if it's the only element, then we just return L. And this makes sense because if it's the only element, the reverse is just that same element, right? You can't flip a list that only has one element in it. And just like that, that's our final answer. Okay, another linked list problem. So this one is about insertion into a linked list. Like I said, insertion into a linked list is one of the big pros of using linked lists. It's easier than insertion into an array. So this one is a recursive insertion method that inserts an element item at position in the original list. And I'll give you a minute to think about it. Okay, let's go over it. So this can be approached recursively because you have the position input and that list input, so we'll make use of that. Step one, as always, is that base case. So if the list is empty, then the item becomes a list. Like if there's nothing to do, then we just create a new int list with our item and call it a day. There are two options for the next step. Either we are at the position where we need to insert, or we are not at that place yet. So if position is equal to 0, if we're at the position where we would need to insert, we adjust the pointers. But we don't have access to the previous pointer, so we need to get a little tricky. Again, this is a singly linked list, so it's a little tricky. So what we're going to do is we are going to create a copy of the node that is currently at that position. So whatever node is currently there, we're going to create a copy of it. And then we're going to change the old node to have our new value. So we created a copy of the node that was at that position with the same head. We set L.tail to be that. So basically we have two of the same node in a row. And then we change the value of the first of those two to be our item. It's a little sneaky. Now in the other case, we want to make our recursive call. So in that case, we just iterate another past the list, so L.tail, and then we keep our item the same. The item doesn't change, obviously. And position goes down by 1 because we're one step closer to our correct position. We also set L.tail to be equal to whatever is returned here because we are returning an int list. Okay. And that gives us our final answer with returning the list, just like that. Now let's do the same thing, but iteratively. So again, I will give you a minute to think about it, and then we'll go over it together. Okay, let's talk about it. So the general framework is the same as the recursive version, so I'm just popping that in. You'll recognize this from the last slide where we have this base case where if there's nothing there, then we just return our new int list item L. If the position is 0, then we insert it in the exact same way. Otherwise, now we have to do something here instead of that recursive step. And then we return L. So here we're going to have to do something a little different. First, we need a pointer to iterate through since we do need to return L. We don't want to be moving through using L because in that case, when we can't return that same L, we won't have the head anymore. We won't have that first item anymore. So we have to create a copy, basically another pointer to that first element that we can now iterate through. And now we're going to loop until we get to the position that we care about. So we're going to loop until our position is 0 and or we hit the end of the list. So we want to make sure we're not hitting the end of the list, and we also want to go until we hit that correct position. And at each step, we just iterate forward and subtract 1 from the position. This can be done in a for loop as well. It's just a little neater to do this in a while loop because there are 2 conditions that we have to do and 2 steps that we have to take. And then now we can create our new node and do the exact same thing we do up here, just down here, setting current.tail to be equal to our new node. Yeah, and this is the iterative way to do that. Okay, we are almost done. Let's get through this. So we're going to do something called shifting a linked list. So imagine that your linked list is more like a circle rather than being a straight line. We're going to take the item that's at the front and we're going to pop it all the way to the end. We're going to do this iteratively. I think that's the easiest way to do it. So I'll give you a chance to try it out and then we can go over it together. Okay, let's go over it. So first things first, if our list is null, there's a lot of things we can't do. So let's just take care of that. It's kind of a base case. We just return null in this case. Now what we want to do is take that int list node that's at the beginning and move it to the end. So first, let's make a pointer and point it at the first, the thing that's going to become the last item. That's currently the first item. And the reason we have to point a different node at this is because we're going to return this int list at the end. And if we iterate with L, we're going to lose that pointer to the beginning of the list, and then we won't be able to return it anymore. So we're just going to create another pointer that points at the beginning and then iterate through. So while current.tail doesn't equal null, then we're going to do current equals current.tail. That's just iterating through the list. Now, once we're at the end, we want to point the tail of the last node at what is previously the first node. So whatever was at the beginning, we're setting the tail of the last node to point at that. And now we want our front int list to point at L.tail. So the second node is now going to be considered the new front. And we want to make sure that L.tail is equal to null because it is now the end. We don't want to be pointing at that second item anymore. And then we just return front, and that's it. Done. Well, that brings us to the end of our discussion walkthrough for this week. I hope you guys have a fantastic week. Please get started on Project Zero, and I'll see you guys next week. Goodbye.